Less than 5 light-years from Earth, there is a planet orbiting another star. Not a theory, not a distant possibility, a real world. It circles a small, restless sun, one hemisphere locked in perpetual daylight, the other in unending night. And it is only one among billions. Our planet orbits an ordinary star in a galaxy containing more than 100 billion others. For most of human history, we did not know whether those stars held worlds of their own. They existed only in equations, in speculation, in imagination. Today, they are detected, measured, and confirmed. We can trace their orbits, estimate their temperatures, analyze the light of the stars they circle. The universe is no longer silent about its planets. In this series, we move beyond our solar system, not to search for life, but to understand how extreme and diverse worlds can truly be. We begin with the nearest known exoplanet. This is Beyond Exoplanet. Just over 4 light-years from Earth orbits Proxima Centauri b. It is the closest confirmed exoplanet ever discovered. In astronomical terms, it is our nearest neighbouring world. The planet circles Proxima Centauri, a small red dwarf star. This star is smaller and cooler than our Sun. It is also significantly more active. Proxima Centauri b completes one orbit in just 11 Earth days. At that distance, gravitational forces have locked the planet in place. One hemisphere permanently faces the star. The other remains in continuous darkness. There is no sunrise here, no sunset. Proxima Centauri b is slightly more massive than Earth, approximately 1.5 times our planet's mass. Surface gravity would likely be stronger. Movement would require more energy. Between constant daylight and darkness lies a narrow boundary region. Climate models suggest temperatures there may permit liquid water to remain stable. If an atmosphere is present, it could redistribute heat across the planet. Proxima Centauri is a volatile star. It releases powerful stellar flares. Radiation frequently floods nearby space. Over time, such activity can erode planetary atmospheres. If Proxima Centauri b retains one, it must be dense and resilient. Atmospheric protection would determine long-term stability. The planet's surface remains unknown. It may be rocky, it may contain oceans, or it may be barren and exposed. From Earth, we see only indirect evidence. Proxima Centauri b may not be hospitable, but it confirms something fundamental. Earth-sized planets exist around the stars nearest to us. Even our closest stellar neighbour hosts more than one world. Proxima Centauri b shows us what exists around our nearest star. But it is only one world in one system. Farther away, we find planetary systems built very differently. 40 light-years from Earth lies the TRAPPIST-1 system, a compact planetary system centered around a small, ultra-cool red dwarf star. 7 Earth-sized planets orbit this single star. TRAPPIST-1 is significantly smaller and cooler than our Sun. Its lower luminosity requires planets to orbit closely to receive warmth. This creates a tightly packed planetary architecture. TRAPPIST-1e is the 4th planet from the star. It lies near the center of the system's habitable zone. Among the 7 planets, it occupies a region where temperatures may allow liquid water. Its radius is close to Earth's. Its mass suggests a rocky composition. Surface gravity would likely be comparable to our own. In scale, it is one of the most Earth-like worlds discovered. TRAPPIST-1e completes one orbit every 6 Earth days. Because the star is dim, close proximity does not necessarily mean extreme heat. Energy balance depends on atmospheric behavior. Like many planets orbiting red dwarfs, TRAPPIST-1e is likely tidally locked. One hemisphere faces constant daylight, the other remains in darkness. Climate models suggest that a dense atmosphere could redistribute heat across the planet. Without circulation, temperature differences would be severe. Balance depends on stability. TRAPPIST-1 is an active star. It produces periodic flares that release bursts of radiation. Over long timescales, such activity can erode planetary atmospheres. Long-term habitability depends on atmospheric resilience and magnetic protection. What makes TRAPPIST-1e significant is not certainty, it is structure. 7 terrestrial planets orbit a single star smaller than Jupiter, some likely too hot, some likely frozen. TRAPPIST-1e occupies a region of relative thermal balance. It demonstrates that compact systems of rocky worlds are not rare exceptions. They reflect a common pattern in planetary formation. Systems like TRAPPIST-1 reveal structural complexity, but the search for Earth-sized planets began with a different discovery, one that changed planetary science. Nearly 500 light-years from Earth lies Kepler 186f. It was announced in 2014. It became the first Earth-sized planet discovered within the habitable zone of its star. Its radius is only about 10% larger than Earth's. In scale, the two worlds would appear remarkably similar. Surface gravity would likely be only slightly stronger than our own. Kepler 186f completes one orbit every 130 Earth days. Its host star is a cool red dwarf. Because the star emits less energy than the Sun, the planet must orbit closer to remain within the habitable zone. Orbital distance alone does not determine surface conditions. Temperature depends on atmospheric composition. Greenhouse gases could retain heat. Without them, the surface could freeze. We do not yet know whether Kepler 186f possesses a thick atmosphere. It may be protective and stable. It may be thin and fragile. That uncertainty defines this world. Red dwarf stars can be active. Flares release bursts of radiation into surrounding space. Over time, such activity can erode atmospheres and reshape planetary environments. Long-term habitability depends on resilience. At 500 light-years away, the light we observe today left the system centuries ago. What we see now is already history. We are not viewing the present. We are observing the past. Kepler 186f marked a turning point in planetary science. It demonstrated that Earth-sized planets exist within habitable zones. Earth-sized planets are not statistical outliers. They are part of the galaxy's structure. Kepler 186f demonstrated that Earth-sized worlds exist in habitable zones. But not all planets evolve towards stability. Some move towards destruction. Approximately 1400 light-years from Earth orbits WASP-12b. It is part of a distant stellar system centered around a star hotter than our Sun. WASP-12b is a gas giant. It is larger than Jupiter. But unlike the gas giants in our solar system, it orbits extremely close to its host star. WASP-12b completes one orbit in just over one Earth day. Its orbital distance is only a fraction of Mercury's distance from the Sun. At this proximity, gravitational forces are intense. The planet is not perfectly spherical. Tidal forces stretch it into an elongated shape. Gravitational interaction with the star distorts its outer layers. Its structure is under constant stress. Surface temperatures exceed 2,500 degrees Celsius. At these levels, many metals would melt. The atmosphere expands under extreme heating. Energy input from the star dominates the planet's environment. Material from the upper atmosphere is being pulled towards the star. Astronomers have detected evidence of mass loss. Gas streams outward under gravitational influence. Over time, the planet may spiral inward. Planetary orbits are not always stable. Tidal interactions can alter trajectories. WASP 12b may eventually be partially or completely consumed. Some worlds do not persist for billions of years. WASP 12b demonstrates that planetary systems are dynamic. They evolve. They migrate. Tidal forces can alter their structure and trajectory. Not all planets are built to last. WASP 12b reminds us that planetary systems are dynamic, but evolution does not always end in collapse. Some worlds offer new kinds of complexity. Approximately 120 light-years from Earth orbits K2-18b. It circles a cool red dwarf star smaller and dimmer than our Sun. K2-18b is significantly larger than Earth. Its radius is about 2.5 times that of our planet. Its mass is more than 8 times greater. It is classified as a sub-Neptune. Sub-Neptunes are not purely rocky worlds. They likely possess thick atmospheres surrounding deep interiors. K2-18b may have a dense gaseous envelope above a high-pressure layer. Its structure is fundamentally different from Earth's. K2-18b completes one orbit every 33 Earth days. Its orbital distance places it within the habitable zone of its star. Under certain atmospheric conditions, liquid water could exist. Using transmission spectroscopy, astronomers have detected water vapor in its atmosphere. This marks a significant development in exoplanet research. We are no longer only measuring mass and orbit. We are analyzing atmospheric composition. Some researchers propose that K2-18b may be a Hycean world, a planet with a hydrogen-rich atmosphere above a global ocean. Such a world would not resemble Earth. There may be no continents, no familiar skies. A thick atmosphere could create high surface pressures. Gravity would be stronger than on Earth. The environment may be stable for water, but not necessarily for complex life. Habitability is not a simple equation. K2-18b represents a new stage in planetary science. It demonstrates that we can probe the atmospheres of distant worlds. The detection of water vapor is not evidence of biology, but it expands the range of environments we must consider. The search for potentially habitable environments is becoming more refined. K2-18b expands what we consider possible, and it is only one example among billions of worlds in our galaxy. 5 worlds. 5 different outcomes of planetary formation. A nearby planet shaped by radiation. A compact system of rocky worlds. A distant Earth-sized milestone. A giant planet under gravitational stress. And a sub-Neptune whose atmosphere we can now measure. All orbit ordinary stars within a single galaxy. The Milky Way contains hundreds of billions of stars. If even a fraction host planets, the diversity we have seen here is only a beginning. For most of human history, these worlds existed only in theory. Now they are detected, measured, characterized, their atmospheres analyzed, their systems mapped across light years. And we are only at the beginning. Beyond our solar system lies not one type of world, but many. This is Beyond Exoplanet. If you want to continue this journey across our galaxy, subscribe and explore what lies beyond with us.